This is the continuation of performance, and this is the next equation which we are going to solve the problem. And the equation is nothing but it relates the number of instructions of the program and the clock cycles required for execution of an instruction. So CPU clock cycle equal to instruction of the program into average clock cycles per instruction. As we have known, CPU time equal to instruction count into CPI into clock cycle time, and CPU time equal to instruction count into CPI divided by clock rate, whereas we have already known the CPU clock time is inversely proportional to the clock rate, so it is substituted as CPI divided by clock rate. By using these formulas, we are going to solve our next instruction. In this, suppose we have to implement the same instruction set architecture. The computer A has a clock cycle time of 250 ps and CPI of 2.0 for some program, and the computer B has clock cycle time of 500 ps, considerably twice of A, and CPI of 1.2 for the same program. Which computer is faster and how much? We have to determine the how many times which system is faster than another computer. For this, we have known CPU clock cycle equal to number of instructions into average clock cycles per instruction. So it is represented as CPU clock cycle equal to I into 2.0 for system A, and CPU clock cycle of B is equal to I into 1.2, whereas the CPU time equal to CPU clock cycle into clock cycle time. So I into 2.0 into 250 ps is the clock cycle time. So 250 ps, which is equal to 500 into I ps. Here, since the number of instruction is not known, we are considering it as I. And for CPU time of B, the same formula, CPU clock cycle of B into clock cycle time, whereas I into 1.2 into 500 ps, it is 600 into I ps. We know the formula for finding how much time the system A is faster than B. While substituting this, the performance of A by performance of B is equal to execution time of B by execution time of A. As we have seen, the execution time of B is 600 into IPS, whereas execution of A is 500 into IPS. So dividing this, we will be having 1.2. So we came to the conclusion that system A is 1.2 times faster than system B for executing this program, in which we doesn't know how many is the number of instruction which is used for execution of this program. So it is generally 1.2 times faster for executing this specific program. And this is the next example. In this, a given application written in Java runs 15 seconds on a desktop processor. A new Java compiler is released which requires 0.6 as many instructions as old compiler. Unfortunately, the increase of CPI by 1.1, how fast can we expect the application to run using the new compiler? We have to find the expected execution time. So expected execution time equal to original time into new number of instruction by old number of instruction. Comparatively, we have to find the percentage of increase of instructions into new CPI by old CPI. So we have given the data of 15 seconds is the original runtime, and new compiler requires 0.6 as many instruction as old. So the ratio is 0.6 and it is 1.1 time increases than old system. So into 1.1. The result is 9.9 seconds. The expected execution time of the new Java compiler which is released will be of 9.9 seconds.